Welcome to the Neural Implant Podcast, where we talk with the people behind the current events and breakthroughs in brain implants in an understandable way, helping bring together various fields involved in neuroprosthetics. Here is your host, Ladan.
Hello, everyone, and welcome to the Neural Implant Podcast. Now, this is one of a series of 3 poster sessions that I was able to record at the NER conference, which is the Neural Engineering. I actually don't know what the R stands for. Nobody ever told me. So this was on the 20th to 23rd of March, 2019 in San Francisco. Really good time. IEEE EMBS conference on neural engineering. Very cool stuff. And unfortunately, I only did the poster session. I only recorded the poster session on the second day, so I only got half of it, and I only pulled out the recording equipment in the end. So I actually saw a lot more really cool pipers that I would have loved to feature here, but they might have been cleaning up or very busy by the time I came around, or it might have been the second day. So hopefully you enjoy this, and hopefully I'll be able to bring you more of these in the future because these are really fun. Do you want to introduce yourself and the name of your poster?
Sure. So my name is Dr. Cary Kuliasha. I'm at the University of Florida, and I work with Dr. Jack Judy. And today I have a poster called In-Vitro Accelerated Aging Assessment of Anisotropic Conductive Adhesive and Implantable Packaging for Bioelectronic Interfaces. It's a mouthful.
Yeah, say that 3 times fast. Yeah, so basically this is reactive age or like accelerated aging. And so you're able to test out basically, 9 months, 6 months, 1 year of what a device would look like inside of a body in days, something like that, right?
Correct, yeah. We're trying to mimic the physiological environment kind of as best as we can from an engineering standpoint and do it rapidly. So our tests, we mimicked about 1 year in the body.
Wow. Yeah, so a few, year and a half ago, 2 years ago, something like this, I had Pavel Tekmakov on the show, and he kind of, started this. And I think it's really good because it's a great way to iterate through designs and make sure, hey, is this device actually something good or not, and is it going to survive in the body? Because the body is a very hostile environment.
Correct, yeah. So with most, accelerated aging environments, it's just saline at temperature. And one of the concerns is that as you heat saline up, the oxygen concentration decreases. But in the body, there are reactive oxygen species that are excreted by macrophages and other immune cells that are trying to destroy an implant. And those oxygen species don't really get mimicked under a standard accelerated aging process. So as you said, Pasha and Kenneth Stokes, I believe, was kind of the original person who years and years ago looked at this kind of with Medtronic. But Pasha at the FDA, he developed what he calls the reactive accelerated aging, which uses a constant replenishment of hydrogen peroxide in your accelerated aging environment to kind of mimic, as best as can kind of be approximated, a chronic inflammatory environment with a concentration of reactive oxygen species.
Okay, and you compared other accelerated aging or heating methodologies as well. Do you want to talk about this a little bit?
Sure. So this entire poster is all about looking at the back-end packaging that implantable devices need. So basically with any device that you implant into the body, we have to electrically connect to the outside body some fashion, either a wireless package or with percutaneous leads. And that packaging can be very prone to failure. And it's a kind of under-researched topic. It's not a very sexy, exciting area to research, but we feel like researching failure of the package is very important. So what we were looking at with our paper, with our poster, is different connector technologies that are used to connect some delicate neural interface with that back-end package. The industry currently uses ball seal connectors, which are used for pacemakers or neurostimulators, and they are very robust and very reliable, but they suffer from, kind of low contacts. They have 8 connections per lead. So in the research environment, what most people use is what's called Microflex technology, developed by Thomas Stieglitz at the University of Freiburg. And that technology basically uses a gold rivet to mechanically and electrically connect a flexible device or, some neural interface with the back-end package. However, there can be some limitations to the Microflex technology, and it's fairly time-consuming to make all these connections because you have to individually wire bond samples. So what we wanted to look at was what's called Anisotropic Conductive Adhesive, which is a type of connector technology that was pioneered by the electronics industry. And it is used with computers and with your phone to connect different devices together. However, these types of technologies were not made for the body, and the body is basically a bag of salt water. And so we wanted to see, how do these devices that are used by the electronics industry correlate over to kind of biomedical implant? So we developed a microfabricated thin film test structure that we could use to basically intentionally short connections together with a printed circuit board using this anisotropic conductive adhesive. And then we can do these reactive accelerated aging tests and longitudinally measure kind of the connections between these shorts with the ACA. And if the ACA fails, we can easily see that electrically by our 10 ohm resistance suddenly jumps to 10 gigaohms or, mega ohms. So it's very obvious when it fails. So we performed these studies. We made a bunch of different samples that we had flexible circuits bonded to printed circuit boards, and we encapsulated the entire package in silicone, which is a common encapsulating material that researchers commonly use. I said commonly already. And we soaked these in our RA environment at 77 degrees Celsius and longitudinally measured the behavior. And the results of this work showed that if we measure the electrical impedance of our package, we saw drastic decreases in the electrical properties, in the impedance of our samples, indicative of water penetration through the encapsulating material into the electronics of our package. That's not entirely unsuspected or uncommon, because silicone is not a great diffusion barrier. But unfortunately, we also saw aggressive failure of our anisotropic conductive adhesive. We did analogous studies in the RAA environment and the accelerated aging environment with no peroxide. And for both of those studies, we had almost 100% failure of our ACA shorted joints in about 4 days at 77 degrees Celsius. So right now, we are a little hesitant with using ACA for biomedical implants or bioelectronics, but we are looking at using different manufacturers. Maybe we chose the wrong manufacturer or, the wrong ACA. So we're going to screen that out and see. But right now, we're a little hesitant to use these for, chronic implants that go on for more than a few months.
So basically, you guys prove that you're wrong, or that this is not a very good thing. So it's actually the very best definition of science, I think, right?
Yes, all of our results were kind of negative, but I feel like from an engineering standpoint, it's much easier to engineer with failure in mind. And if we have failure, we can fix it, hopefully, with the right time, with the right science and the right engineering. If you never see failure, then you really don't know where to improve your product.
Yeah, definitely. That's the best way to do it. And you were talking about some people think this is too aggressive of a test.
Correct. I believe one of the quotes that I heard today was, "Oh, of course your samples are failing because you're basically shooting it with a machine gun." It is true that right now we do not know how well RAA environment actually mimics failure in the body. Pasha Takmakov, who developed this setup, he has an awesome paper that he published in, I think, 2015 that was looking at different cortical implants for bioelectronics. And he showed that there was failure mechanisms that were taken from explanted samples from the brain that could be replicated in the RA environment. So he showed that there is a correlation. However, we don't know kinetically really if our acceleration factor that we use is at all accurate. And we don't know if the RA environment might just be too aggressive. We might be unnecessarily destroying our samples, and they might not actually experience it in the body, but we have plans to test that out.
Yeah, better to over-destroy than under-destroy. Better to over-engineer than under-engineer. What is that factor, actually?
Right now, let's see, I think off the top of my head, I think it's for every 10 degrees Celsius increase in temperature, it's a 2 times acceleration factor. So the body's at 37 degrees Celsius, and we're testing it at 77 degrees Celsius. So I think 24 days in the body, or in vitro study, mimics about 1 year in the implant environment, approximately, give or take a little bit.
Wow, that's awesome. That's really cool. And I really like it because you can really iterate devices and really make sure that you have the best one and iterate through materials and basically save yourself years and years of experimentation.
That is our hope.
Okay, so what are the next steps with this?
So we're looking at different manufacturers to try to see, is this failure that we found for our one type of ACA, is that just a universal thing that all ACAs experience? And if so, maybe ACA should not be used. And depending on, what sort of grants we get and how we go about this, it's theoretically possible to make your own ACA that does not have this hydrolytic instability, But we're now pursuing alternative connector strategies that don't rely on ACA.
Sounds good. Is there anything that we didn't talk about that you still want to mention?
I don't think so. I think this is very thorough.
Okay, sounds good. Thank you so much.
Thanks.
Hope you enjoyed the show and were able to learn something new, bringing together different fields in novel ways. Until next time on the Neural Implant Podcast.